We did that in anticipation of the arrival of something called a coronal mass ejection, or CME for short, this blast of solar material in the form of strong magnetic fields and charged particles. And when they arrive here at Earth, they can escalate activity up, especially if they're quite strong.
Slowly but surely, colours began to appear on this beach in Brittany. The sky above the Noirmoutier Bridge in the west of the country also lit up. Vibrant scenes that were visible in a string of locations across France and beyond.
A solar storm doesn't announce itself to your phone. It hits, and suddenly GPS can get shaky, radio can act weird, and some satellites have to switch into safe mode. The punch is invisible, but the damage can still be real. Here's the twist. Earth can get a warning because we can post a guard in front of the planet. Not in Earth orbit, not on the moon, but out in deep space on the Sun-Earth line. That guard stands watch at a place called L1. L1 is often described as a parking spot in space, but don't let that cute phrase fool you. If you build the right tools there, sensors, antennas, navigation beacons, you can shape what everyone else can safely do near Earth and the moon. That's why some people say whoever controls L1 and L2 controls the Earth-Moon economy. But control doesn't mean planting a flag and calling it yours. Space law doesn't work that way, and gravity doesn't either. The real fight is quieter. Who builds the routes, the rules, and the services that everyone ends up relying on? To understand the stakes, you need the simple idea first. A Lagrange point is a place where gravity and motion balance in a special way. If you put a spacecraft in the right kind of path near that spot, it can stay lined up with two big bodies, like the Sun and Earth, using less fuel than you'd expect. There are 5 main Lagrange points in a two-body system, labeled L1 through L5. L1 sits between the two bodies, and L2 sits just behind the smaller body. L4 and L5 lead and follow in the orbit like two steady companions. Now the detail that matters. L1 and L2 are useful, but twitchy. They're not naturally stable like a bowl you can roll into and rest. They're more like balancing a pencil on its tip. You can do it, but you must keep making tiny corrections. So when people say park at L1, what they usually mean is to orbit around the L1 region in a looping path, like a halo. You're not sitting on a dot, you're riding a carefully chosen route that stays nearby. That nuance is the difference between science fiction and real spaceflight. Sun-Earth L1 is far, about 1.5 million kilometers from Earth, toward the Sun. That distance is the whole point. The solar wind reaches that guard post before it reaches us. That's how you buy precious lead time. This isn't a theory. On December 2, 1995, the SOHO spacecraft launched to study the Sun, and it has worked near the Sun-Earth L1 region for decades. It helped scientists understand solar activity and watch events that can affect Earth. Then came spacecraft like ACE, designed to study energetic particles and solar material from the Sun-Earth L1 point. When you're trying to understand what the Sun is throwing at Earth, you want to measure it upstream before it slams into our magnetic shield. And the world keeps doubling down on this idea. NOAA's SWFO L1 plan is built around non-stop space weather watching from this same L1 neighborhood, feeding data to forecasters. In plain language, L1 is becoming part of Earth's early warning system. If L1 is the lookout tower facing the Sun, L2 is the quiet back porch, still close enough to stay aligned with Earth, but far enough to keep things calm. At Sun-Earth L2, the Sun, Earth, and Moon stay on one side, which helps telescopes stay cold and shielded. That's why the James Webb Space Telescope went there. Webb doesn't sit on L2, it flies a halo orbit around it, keeping its sun shield between its instruments and the heat and light of the inner solar system. That stable heat environment is gold for infrared astronomy. Even Webb's numbers show how real this is. Its orbit around the L2 region is a large loop, and its distance from the L2 point changes over time because it's following that halo path. That's not trivia, it's proof that L2 is a region and an orbit family, not a single parking stall. So now we have a pattern. L1 is where we watch the Sun for danger. L2 is where we build deep space observatories that need quiet, cold conditions. These aren't empty points on a diagram anymore. They're becoming addresses we keep returning to. Here's where the title earns its teeth. The Sun-Earth system has L1 and L2, but the Earth-Moon system also has its own L1 and L2 regions. Different locations, different uses, different stakes. It's like discovering there are two sets of choke points stacked on top of each other. Earth-Moon L1 sits between Earth and the Moon, closer to the Moon than Earth. Earth-Moon L2 sits on the far side of the Moon, in line with Earth and Moon. If you're trying to move between Earth and lunar space, these regions can act like highway interchanges. This is not just a poetic idea. Engineers actually design routes that use these regions. In advanced mission design, trajectories can be built to take advantage of the gravity balance near these points, sometimes saving energy compared to brute force paths. Now add one more layer. The Moon's far side is famous for a simple problem. It can't see Earth directly. If you want steady communications for far-side missions, you need clever orbital choices and relay systems. Earth-Moon L2 family orbits can help keep lines of sight that a low lunar orbit might lose. That's why you keep hearing about orbits around the Earth-Moon L2 region, even when the spacecraft isn't sitting exactly at L2. NASA and partners have studied near-rectilinear halo orbits, or NRHOs, linked to the Earth-Moon L2 family because they can support access, navigation, communications, and stability. And this is where the economy enters the story. If we build a future where robots mine, astronauts build, and companies operate around the Moon, then someone must provide the basics: comms, navigation, tracking, and safe routes. The L1 and L2 regions are natural places to anchor those basics. In movies, control looks like lasers and flags. In real life, control often looks like a service everyone quietly depends on. The internet isn't ruled by one king, but the world still depends on key cables, routing hubs, and standards. Space is heading the same way. The US government's own cislunar strategy talks openly about building communications and positioning, navigation, and timing capabilities in cislunar space, and doing it in scalable, interoperable ways. That's a blueprint for shared infrastructure, and shared infrastructure becomes power. It also talks about extending space situational awareness, basically the ability to know what objects are where and to operate safely as traffic grows. If more spacecraft crowd the Earth-Moon neighborhood, the groups who can track and share data will shape what safe even means. And then there's the sneaky one: time. The 2024 Cislunar Action Plan discusses creating foundations like coordinated lunar time and lunar reference systems, because you can't run navigation, docking, mapping, or trade without everyone agreeing on the same clock and grid. Standards don't sound like conquest, but they can decide who plugs in easily and who struggles. Space law adds another twist. The Outer Space Treaty says outer space is free for exploration and use, with free access. And it also says space isn't subject to national appropriation, no simple land grab. So owning L1 or L2 is not the game. But the same treaty also talks about acting with due regard for others and avoiding harmful interference. In a crowded future, harmful interference can include blocking a key line of sight, jamming signals, or creating unsafe traffic conditions. The choke point isn't about territory, it's about operations. So the real question becomes, who builds systems at L1 and L2 that the rest of the world wants to use or has to use to stay safe? That's how control shows up, through reliability, coverage, and trust. Now we can finally translate the title. The 1,000-year war for L1 isn't one non-stop battle. It's a long competition across generations, like shipping lanes, canals, rail hubs, or data networks. The winners aren't always the loudest. They're the ones who become essential. Step 1 is the easy part: put a spacecraft near L1 or L2. We already do that at Sun-Earth L1 and Sun-Earth L2. The hard part is step 2. Build a whole ecosystem: relays, navigation aids, docking standards, tracking, and emergency rules so that many missions can operate together without chaos. Step 3 is where it starts to feel like control. If a company's cargo tugs or a nation's lunar comm network becomes the easiest path through the Earth-Moon system, then other missions will route around that reality. Not because they're forced, because it's efficient, safe, and already there. And here's the emotional hook beneath the math. This isn't just about rockets. It's about what comes after rockets feel normal, when the Earth-Moon system becomes a place people actually work. In that world, L1 and L2 aren't trivia. They're the intersections where the whole map starts to bend. If you want a grounded example, go back to space weather. The reason we care about a space weather sentinel at L1 is simple. Modern life runs on satellites, timing signals, and electrical systems that can be affected by solar activity. L1 is where we put the smoke detector. Now stretch that logic into the Earth-Moon future. If we build reliable comms and navigation around lunar Lagrange regions, then getting to the moon stops being a heroic one-off and starts looking more like transportation. That's when an Earth-Moon economy becomes possible, because you can plan, insure, coordinate, and operate routinely. And that brings us back to the claim. Whoever controls L1 and L2 controls the entire Earth-Moon economy. Taken literally, it's wrong. No one owns those points, and physics won't obey a flag. But taken as a warning about infrastructure, it's sharp. Whoever becomes the trusted provider at those intersections can shape what the rest of the system feels like. So the war might look boring from the outside. It will be bids, launches, standards meetings, navigation networks, shared catalogs, and long, quiet engineering work. But if humans truly expand outward, that boring work could decide who sets the pace for a very, very long time.